And it's my pleasure to introduce one of the keynote speakers for the second year project showcase. That is Thomas Moynihan. Thomas is the authors of one of, I think, one of the most significant books of past year or so, X-Risk, How Humanity Discovered Its Own Extinction. One of the key ideas of the book is the distinction that Thomas makes between apocalypse and extinction. Apocalypse is a story. It is an old story. There's a view that the end of the world, as in the life world of a culture, is so linked with the end of life on Earth, or with the end of the life of humans, that the latter, that is the end of life, is seen as a function of the former. That is, apocalypse is the end of the world as a meaningful event inside of a cultural narrative. Apocalypse is, at its core, a religious concept. It is theodicy. It is eschatology. The far more recent and frightening discovery, really only a few hundred years old or so, is that extinction is not eschatology. Extinction is not a meaningful end. It is the end of meaning. The terraforming, as I see it, is concerned not so much with eschatology, though much of the contemporary Western environmental movements certainly are. It is concerned much more so with the conditions of extinction, as both as simultaneously an ecological, epistemological, and ethical catastrophe, which is, again, not the same thing as interpreting the meaningfulness of that end. In fact, as I discuss in the book, The Terraforming, the human capacity for meaning making is at least as much, if not more, responsible for the predicament in which we find ourselves as technological intervention, as the key driver of this situation. The elevation, if you like, of meaningfulness as a noble end in and of itself. That the experience of experience is and the contestation of meaning, symbolically, of land, of people, and cultures, is a good in and of itself. This is the engine of the anthropodynamic machine that is destroying us all. So Thomas will tell us much more about this. What is at stake in terms of the discovery and conception of deep time, as the basis of this, the intellectual and scientific theory of extinction, and what it has to do with the deep future, hopefully, of which there is far more than the past. Thomas is a researcher based at Oriel, completed a PhD recently at Oriel College at Oxford, and is now currently working with the Oxford's Future of Humanities Institute. So I introduce, with pleasure, Thomas Moynihan.
Yeah, good. Thanks. Yeah, thank you so much, Benjamin. Yeah, thank you. That was a very kind and generous introduction. And thank you to the whole Strelka team for organizing this. Also, particularly thank you to those two previous projects. Absolutely mesmerizing, both in very different ways. But yeah, I'm hoping what I'm going to talk about today might touch on some of the themes, particularly atomic energy, and also the contingency of evolution, and the ways in which intelligence can manifest. So yeah, without further ado, I'm going to share my screen because I'm doing a presentation. Excellent. So I hope you can see the presentation. You're probably all familiar with the way they look these days. Great, thank you. Yeah, so today I'm going to talk a bit about escaping the planet, which has obviously been a topic on people's minds these past weeks for obvious reasons. But I want to talk a bit about the historical pedigree of that idea and some of the more positive ways in which it's been articulated. So yeah, I want to recount some of the story of how throughout history people have woken up to the idea that in the longer run, leaving the planet may be of interest to humanity. In fact, I want to explore the ways that people have framed this precisely as a liberation. So to back some of that up, first, what is liberty here? So as a working definition, let's say that liberation is the increase in autonomy or the ability to maintain and expand options and set one's own ends. Whereas heteronomy, the opposite, is the decrease in liberty alongside loss of options and potential to fulfill ends. Remaining Earth-locked brings severe heteronomies for the human species in the longer run, compared to what might be achieved beyond Earth. And so the following is the history of how certain people woke up to these heteronomies and suggested ways to escape and unfetter ourselves of them. So today I'm going to try and weave together a few themes that have grown together across the history of thinking about the long-term future. These are liberation from scarcity, whether of resource, as Earth only intercepts a fraction of the sun's total energy output, or of time, as Earth has a finite future window of habitability in the very long term, and ultimately, therefore, liberation from extinction. Extinction indeed is the ultimate heteronomy, the loss of all options for our collective future. As we shall see, it's since the late 1800s that multiple visionaries have arrived at the idea that space equals survival. This is why leaving Earth would be an ultimate jailbreak. Put positively, I hope to explore how the upper bounds of what humanity can achieve and how long it might last to fulfill this have exploded exponentially throughout the past few centuries, and how this growth has moved in lockstep with ambitions to unbind life and biology from Earth. But pursuing liberation obviously first requires recognizing that one's situation is one of bondage, penury, or privation. However, for the majority of history, at least in the West, people could not see that leaving the planet and expanding this foothold of intelligence and life would be liberating, precisely because they did not apprehend the scarcity of intelligence and life within the wider cosmos. Why? From the ancient Greeks to the medieval Christians, there was a common intuition that the universe is optimally designed for life and thus is maximally and invariantly populated throughout time. From Aristotelian to Epicurean cosmology, there was not a recognition that vast regions in both time and space could be or had been abiotic or unpopulated. When the Copernican revolution rolled around and the scientific revolution revved up, this didn't change. Natural philosophers commonly assumed that the Copernican universe was fully habitable and inhabited. If other planets revolved around other stars, they also harbor life and intelligence. They insisted they would seem a massive waste of real estate otherwise. To give some brief examples, Christian Huygens wrote at the end of the 1600s, there would be madness to allow the planets of other suns to be nothing but vast deserts, lifeless and inanimate stocks and stones, and deprive them of rational creatures. Many also presumed that the other planets were populated with creatures essentially identical to us. Others were sure that if humanity dies here on Earth, it will inevitably appear or persist somewhere else in the infinities of the cosmos. Later, in the 1840s, the theologian Thomas Dick attempted to produce a census of the population of the solar system. He assumed that every single last piece of surface area in the system must be populated, even the rings of Saturn. Extrapolating from the population density of England, which was 280 inhabitants to a square mile at the time, he scaled this up to the whole solar system and arrived at a number of 21 trillion. He didn't stop there. Later, he guesstimated the total population of the entire visible universe at the time and put it at an ample 60 quartillions. Because of this outlook, no one acknowledged that the end of the Earth would simultaneously spell the end of human life or civilization. There was similarly no motivation to imagine humanity migrating to other planets to bring life to an otherwise non-living cosmos. In such a situation, where the universe is invariantly full of life, independently of human actions, there was little reason to make ethical arguments for humanity or life spreading beyond. It would produce little consequential benefit, since the cosmos was already full of humanoid life and value. Of course, there were, since Kepler, fictional visions of interplanetary visits and even conflicts or conquests. but no concern for prolonging intelligence's future by settling unsettled places. People envisioned trips to occupied planets, but never the permanent settlement of otherwise entirely uninhabited spaces. All in all, many simply assumed that humans, or at least beings identical to us, exist on all the other planets. There was as yet no PENURY, no planetary specificity, and thus existential fragility that could serve as bondage to be liberated from. Nonetheless, the idea of a scarcity of future time based on secular physical process rather than divine decree or orchestration had begun to consolidate in the latter 1700s. Around this time, the first scientific estimates of the future window of planetary habitability emerge. For example, in the 1770s, George Buffon performed some rudimentary thermal experiments and estimated that there were 93,000 years left until Earth loses all its internal heat and becomes uninhabitable. But Buffon also believed in life on all the other planets throughout the cosmos. He also believed in organic molecules that suffuse the universe and are indestructible. Individual species may be locally suppressed, he said, but the total amount of organic matter remains universally constant because of these indestructible seeds. Life is here ontologically basic and thus permanent. Individual planets freeze and become uninhabited, as the Earth one day will, but there will always be habitable planets and thus life. Such views were commonplace. There was not yet an idea that life, as a whole, may have had a beginning, in the sense of a genuine beginning, localizable in both space and time. It was just assumed to be part of the cosmic fabric, always has been, always will be. This outlook cannot accommodate the insight that the entirety of present biodiversity may flow from, and thus be causally dependent upon, one occurrence in the arbitrarily distant past. An occurrence that, because it hasn't observably happened again since, supports the further inference that it may be unlikely to reliably occur again. The sense was not that life began once long ago and potentially on one precarious planet, but that it is continuously beginning anew everywhere and everywhen. Indeed, if organic seeds are suffusing the void anyway, why bother attempting to spread it ourselves? Nonetheless, natural histories like Buffon's instilled the sense of a future deadline for at least terrestrial humanity. Moreover, since they also put an end stop on past habitable time, they helped dispel the sense that, at least on Earth, everything achievable had already been achieved in the immeasurable past. In other words, such ideas provided the suitable physical backdrop for emerging theories of social progress and technological novelty. Combining these insights, Marquis de Condorcet wrote in 1794 that the progress of humanity's perfectibility has no other limit than the duration of the globe upon which nature has placed us. Condorcet and others were optimistic about humanity's prospects. Their sense of our headroom for improvement was prescient, but they were also very naive about the inexorability of our descendants achieving such heights. In an 1843 satire of such utopian confidence, the American essayist Henry David Thoreau decided to beat the utopians at their own game. He wrote, "Perchance coming generations will not abide the dissolution of the globe, but availing themselves of future inventions in aerial locomotion and the navigation of space, the entire race may migrate from Earth to settle some vacant and more clement planet." Though intended in jest and scorn, this is perhaps the first place someone suggested interplanetary settlement as a means for human survival. Arriving in the mid-1800s, the science of thermodynamics drastically heightened this sense of a scarcity of future terrestrial time. Hermann von Helmholtz and Lord Kelvin provided a theory of stellar evolution based on gravitational collapse that professed to be able to put numbers on solar lifespan, past and future. The theory was that the sun was contracting and cooling. Kelvin spoke of a past when the Earth was tenantless, and of a future when it can no longer be a habituation for man or any living creature. In 1854, he estimated only 300,000 years of future life. Forecasts varied between physicists, but by the closing decades of the 1800s, the community converged upon the very low tens of millions. The solar system's future was not all too long. Expressing the general mood in 1893, the Irish astronomer Robert Ball pronounced that our sun has already dissipated about 4/5 of the energy with which it may have originally been endowed. The millions of years that our descendants had left could likely be counted on the fingers of one hand, he ventured. Moreover, extreme confidence in the inevitability and commonality of humanoid life had come into question after the Darwinian Revolution. In 1884, the astronomer Simon Newcomb looked back to the works of Thomas Dick and his Panglossian population census for the universe and took aim at the naivety of such reasoning. He wrote that Dick's naivety may be seen by reflecting on the brevity of civilization on our globe when compared with the existence of the globe itself. Using the knowledge of the time, he wrote that the Earth has existed for 10 million years, humanity for 10,000, civilization for 4,000, and telescopes for less than 200. He wrote, supposing an angel visited at intervals of 10,000 years to seek for thinking beings, he would have been disappointed 1,000 times or more. Reasoning by analogy, we are led to believe that the same disappointments might await him who should now travel from planet to planet and from system to system on a similar search until he examined many thousand planets. It is within this context of increasing sensitivity to the potential rareness of intelligence that images began to take hold of future humanity migrating inward within the solar system to warmer planets as the sun shrinks. Take, for example, H.G. Wells' words at the end of 1897's War of the Worlds, where he suggests that when the slow cooling of the sun makes this Earth uninhabitable, humans may migrate to inner planets like Venus in order to huddle around the dying stellar ember. However, such intrasolar diaspora only prolongs the inevitable. Others had started to look beyond, but crude interstellar flight still seemed beyond the realms of plausibility. In 1900, Nikola Tesla cited Kelvin's pessimistic estimates for the sun's future lifespan and implied an ingenious solution. He wrote, "Do not let us despair. There will be a chance to kindle a new life on a distant star. This wonderful possibility can be achieved if germs of organic life may be transmitted through interstellar space." Here we seem to be getting some of the first proposals for what we now call directed panspermia. The hope might have been that these seeds would find a home and perhaps eventually re-evolve into something like humanity. Surprisingly enough, the intuition that reruns of evolution would reliably end up in something humanoid remained prevalent at this point in time. However, as the 1900s dawned, biologists began, for pretty much the first time, explicitly cautioning that reruns of evolution on other planets are possibly very unlikely to recreate anything recognizably intelligent, let alone humanoid. As this realization dawned, it may have seemed that the fate of humanoid intelligence was indeed locked to the sun, and there was no longer any secure guarantee there was any intelligence beyond. All in all, as the 1800s drew to a close, there was seemingly not the power source to take humanity itself to other stars, nor was there any known power source to prolong the sun beyond a few 10 million years. The outlook was somewhat bleak. Then, just as the 1900s dawned, came the discovery of radium, radioactivity, and the power locked within the atom. This revolutionized everything. The sheer amount of energy locked up with the atom was truly astonishing at the time. Accordingly, Frederick Soddy, one of the fathers of nuclear physics, had in his 1912 classic, The Interpretation of Radium, felt warranted to suggest that once a civilization unlocks atomic power, it may explore the outer realms of space, emigrating to more favorable worlds. The year earlier, in 1911, Tsiolkovsky had cottoned on to the revolutionary potential of radium. He wrote that if it were possible to sufficiently accelerate the decomposition of radium, then its use could give such a speed to a jet device that reaching the nearest star would be reduced to 10 to 40 years. A pinch of radium would be enough for a ton rocket to sever all ties with the solar system. As opposed to slipshod and haphazard directed panspermia, crude interstellar migration had seemingly come within the remit of scientific plausibility. Tsiolkovsky announced explicitly that this would liberate us from the iniquity of extinction. It would decouple the future lifespan of civilization from that of the sun. Humanity could migrate from sun to sun, which rebukes the gloomy views of scientists such as Kelvin, he added. 6 years later, the forefather of US rocketry, Robert Goddard, arrived at the exact same conclusion. Can intelligence outlive the sun that birthed it, he asked. His optimistic answer was yes, if it is possible to unlock and control intra-atomic energy. If we cannot do so, he suggested sending out organic protoplasm to seed other planets. So, the discovery of atomic energy dramatically heightened headroom on what we might achieve. But at this point, from the perspective of 1918, all bets were off as to whether the atom could be unlocked, and if so, how long it might take to master. However, the discovery of atomic energy also drastically expanded timescales within which unlocking it could be attempted. As one science writer remarked in 1906, the discovery of this new form of energy has extended indefinitely the backward and forward sweep of the cosmical timetable. Geologists pointed to the Earth's internal fund of radiogenic heat. Physicists started speculating upon subatomic processes sustaining the sun. Either way, it seemed that the Earth could remain habitable for orders of magnitudes more than previously expected by Victorian physicists. Radium came to the rescue, as various journalists put it. Amongst certain scientists during the 1920s and 1930s, this instilled a strong sense of responsibility towards the dramatically extended future. In a sense, increased estimates for future habitability liberated them from parochialism regarding their potential position in time, just as cosmopolitanism had liberated people from chauvinistic attachment to blood or soil in space. The US geologist Thomas Chamberlain delivered a speech in 1908 that is worth quoting in full. He said, "Giving thought to the resources that affect our future appeals to me with peculiar force, for my studies of the past decade have led to the belief that the era of the Earth's future habitability is vastly greater than we have been wont to think. We have grown up in the belief that the Earth sprung from chaos at the opening of our era and is plunging on to catastrophe or to a final winter in the near future. Quite at variance with this, I have come to believe that it offers a fair prospect of fitness for habitation for ages yet to come. If this be true, it is eminently fitting that our race should give a due measure to thought to the ulterior effects of our actions. The probabilities of the figure are at least so great as to render imperative the serious consideration of our obligations towards this future." Not long after, the physicist Sir James Jeans provided an estimate of 1 trillion years for future terrestrial habitability. "As inhabitants of the Earth, we are living at the very beginning of time," Jeans announced. He was, of course, rather optimistic with this estimate. Later, mid-century, it was revised down to 10 and then 5 billion years, when a greater understanding of the nuclear processes within stars was garnered. And since the 1970s and 1980s, it has been revised down further to around 1 billion years of future terrestrial habitability, due to growing understanding of processes and sensitivities within the Earth's own atmosphere. But this doesn't matter. Jeans's estimate is important because it encouraged people to start realizing that civilization's future prospect may be orders of magnitude longer than the whole human past, or at least there is nothing in science to suggest this impossible. But possible, again, does not mean inevitable. As Chamberlain stressed, extended congeniality of conditions does not ensure actual realization. Jeans also noted that the entirety of this future could be tragically truncated. He stressed in 1929 the responsibility this places on us, because we are drawing plans and laying foundations, he said, for a longer future than we can well imagine. But should humanity ever unlock that atom in the multiple billions of years left on Earth, then perhaps it may spread beyond this solar system, in which case the upper bound on the human descended future grows again, and so too does our responsibility accordingly. In 1935, Bertrand Russell relayed that the progress of scientific knowledge had made it at the very least doubtful as to whether there is life anywhere else. This therefore means that it might die out with our planet. Citing Jeans, he claimed that we have 1 trillion years left in which to invent a way to travel to another star with habitable planets, so as to safeguard the future of life and mind in what might just be the whole galaxy. He wrote, "It is perhaps a send of hope, but let us make the best of it." Of course, a few years later, the atom was unlocked, and ironically, the hope that atomic power had once promised for a much lengthened future was, after the Trinity test of June 1945, muddied by the fear that it was putting the entirety of this future in danger. So too, in the 1950s, did the rocket technology that had once promised a radically prolonged future begin putting that entire prospect in jeopardy too. nations developed intercontinental missiles. So how much might really be on the line? In other words, just how big could the future really be should our descendants actually truly become post-planetary? The first quantitative estimate on its upper bound was supplied by JBS Haldane, a friend of both Jeans and Russell. Already in 1926, in an astonishing text on the far future, he had put a rudimentary number upon the upper bounds of longevity for a civilization that becomes truly interstellar. He imagined a civilization hopping from star to star and thus surviving for the future lifespan of the whole galaxy. Using the physics of the time, he put this at a whopping 80 trillion years. At the time, this was based on little real science, but it serendipitously matches up with today's estimates, which predict that the Stellariferous era will end in approximately 100 trillion years. What's philosophically interesting here is that Haldane was not forecasting eternal life. He was hinting to upper bounds that are enormous but finite. Indeed, it was always infinities or eternities that prior thinkers, for generations, had fallen back on when insisting that life is invariant and indestructible within the universe. They had argued that whatever is lost will eventually return elsewhere and elsewhen, because within eternity all the possibilities inevitably recur infinitely. Assuming this to be true, there cannot strictly be any meaningful sense to there being more or less future generations. Moreover, everything good that we might yet accomplish has inevitably already been accomplished limitless times, such that any of our achievements moving forward cannot inflict meaningful change on the whole. However, this age-old view suffered a fatal blow in the 1930s, when evidence began building that the universe was expanding and thus seemingly had a definite beginning. For various reasons, expansion also seemed to imply an upper limit on what might be achieved in the future, whether via heat death or galactic recession or causal isolation. Arthur Eddington had spelt this out as early as 1933. And this is important because, in opposition to the amorphous eternity where everything returns, a genuinely irreversible cosmic history implies that intelligence might be able to effect a meaningfully consequential and beneficial change on the total amount of value that will have ever been realized in this effectable universe. Suddenly, the value of ensuring more or less future generations can come into focus. Particularly, that is, when you realize that ensuring the existence of the lion's share of these potential future lives and the meaningful experiences that they might experience is gated upon intelligence leaving behind the sun that birthed it. So, to sum up and wrap up the story of this talk, the historical emergence of ethical arguments for space settlement arose from the slow recognition that the wider universe is likely not maximally full of life and intelligence. In fact, as time has gone on, evidence has instead mounted that it may be extremely empty. Empty, yet capable of supporting vastly more life, more diversity and vibrance than its currently sterile state. Moreover, the universe has also gained a beginning, which put a backward stop on the amount of time within which prior intelligences from elsewhere might have already existed and achieved everything achievable. This makes it at least conceptually plausible that we are living in a cosmic epoch before intelligence of whatever kind becomes a wide-scale factor at meaningful scales. It also meant that if, for whatever reason, there is also some forward limit on what is achievable, no matter how large, then we can apprehend that it is also at least plausible that in the far future, intelligent minds may be able to consequentially affect the total amount of meaningful activity that will have been achieved in this cosmos. One might thus think of intelligence, wherever it may have been born, as a kind of nucleation of a crystal from a solution, a primary seed, tiny and fragile at first, but charged with the potential to tip the entire system into a dramatically new state. Perhaps it could be the spark plug or the catalyst that triggers the shift from an abiotic to a biotic universe. But whether our descendants get the option to even attempt this, or to even exist at all, rests entirely on the actions of people currently alive in the here and now. As the past weeks have demonstrated, of the many of us currently living, only a privileged few are likely to ever have the opportunity to exit Earth's atmosphere. But our collective actions, rippling forwards, will determine whether this situation may change in the future. because the current generation's decisions influence whether there will be a viable future at all. Seen this way, we living are perhaps the empowered few, and the unborn the disenfranchised many. If humanity ever eventually does become starfaring, we may be living during the very first infinitesimal of civilization's entire history. The peaks of what can be achieved in arts as much as science lie in that future. Most of intelligence's potential remains out there, but there is not necessarily a rush to reach it. Our immediate priority, here and now, should be safeguarding it and charting a course that ensures that we do not permanently lose the opportunity to later try. Thank you.